Good morning friends. In this lecture I will introduce you to the basic of radiative heat transfer. So, just like in conduction and convective heat transfer we talk about heat flux. In this radiative heat transfer we also talk about heat flux. So, emissive power of a surface is defined as emitted energy per unit time per unit surface area. However, unlike conduction and convection, the radiative energy is emitted in all the directions. So, for example, if we have a surface, a flat surface, the energy will be emitted in all the directions. So, in this case of flat surface there are total 2 pi solid angles. So, the energy will be emitted in 2 pi solid angles. The units of emissive power will be watt per meter square. Okay, so, this is the total energy that is emitted by a surface in all the directions. Now, we know that the radiation it's dependent on its color. Now, color of radiation is decided by its wavelength. Some people use frequency and some people use wave number, but in this course we will be mostly dealing with the wavelength. So, we define spectral emissive power as emitted energy per unit area per unit time in a given wavelength. Okay. So, the units of this will be watt per meter square per angstrom. Okay. So, where angstrom is the selected unit for wavelength. So, we will discuss this in detail in later lectures. Sometimes we will be using microns, sometimes we will be using angstrom, but mostly in heat transfer community angstrom is the usual unit for wavelength. So, the total energy in a spectral wavelength lambda will be watt per meter square per angstrom. Okay. So, this is a monochromatic radiation, we call it monochromatic radiation. Now, another concept of radiative heat transfer which is very important is the concept of black body. In daily life we define a black surface as one which does not reflect radiation. So, how do we see any body? So, the sun radiation falls on a surface and then the reflected radiation from that surface reaches to our eye, and if any surface by chance does not reflect the radiation, the solar radiation or radiation from any light source, then we say that the surface appears to be black, because the entire radiation is absorbed by the surface and this surface is called black. Now, the interest in black surfaces basically arose with the research in the area of solar radiation. So, our sun which behaves pretty much like a black body at a temperature of 5777 Kelvin, it behaves like a black body. So, later on researchers tried to fit some mathematical relation to explain the radiation behavior of sun. So, Rayleigh, Lord Rayleigh, Jeans, Wien, a lot of scientists tried to explain how the solar radiation behaves, and then later on Max Planck basically came up with this mathematical relation which we now known as Planck function or black body emissive power, and this relation is given by this relation in frequency and also in the wavelength region. Okay. So, it depends on number of parameters. So, what basically Max Planck did, he applied the concept of statistical mechanics and quantum mechanics, and he came up with this mathematical relation based on the principles of quantum quanta, that the energy levels they undergo transition at selective wavelengths and in quantized states. So, he came up with this expression of the Planck function, and what basically this represents is energy emitted by a black surface at a given wavelength in a per unit time. So, this is basically the Planck function or black body emissive power. Now, as I told you, some people some researchers they prefer the units of frequency. So, nu is the frequency here, while some other researcher would prefer lambda, which is the wavelength, and these two units are basically related with the speed of light. So, frequency is related to the wavelength, nu is equal to c lambda, where c is the speed of light. Okay. So, we can basically convert from different units, that Eb nu in frequency units we can convert it into Eb lambda. Okay. So, the various constants used in the explanation of this Planck's law are Boltzmann constants k. So, K is 1.3807 into 10 to the power minus 23 joule per Kelvin, this is the Boltzmann constant. Then we have Planck constant H. Okay. So, here we have defined number of constants C1, C1 is basically 2 pi s c naught square, c naught is the speed of light in vacuum. So, this constant has value 3.7418 into 10 to the power minus 16 watt per meter squared, and it is called first radiation constant. Then we have defined another constant C2, which is s c naught by K. H is again Planck constant, K is Boltzmann constant, c naught speed of light. The value of this is 14388 micrometer Kelvin, it is called second radiation constant. So, there is quite an advantage of non-dimensionalizing the black body emissive power. Now, we will see how this black body emissive power varies with the spectrum, with the wavelength. Okay. So, on this slide you see two curves. On the left curve, what you see is basically the black body emissive power, variation of black body emissive power with wavelength. On the x axis we have wavelength, and there are number of curves on this, each representing the temperature. So, we have plotted these curves as a function of wavelength for different temperatures, and what we see here is that the intensity, the peak value of the emissive power increases as we increase the temperature. Okay. So, the peak value is increasing in this direction as we increase the temperature. Furthermore, what we observe is that the peak is shifted towards the left. So, when we are increasing the temperature, the peak is shifted towards the left, and this is something we already know, what we basically know by the Wien's displacement law, that is the maximum energy emitted by a black surface shifts towards smaller wavelengths as we increase the temperature. On the right side of this slide, what you see is basically the non-dimensional emissive power as a function of the parameter n lambda t, where n is the refractive index of the medium, lambda is the wavelength in angstrom, and T is the temperature, lambda is in the micrometer and T is the temperature in Kelvin. So, on the x axis is this parameter and lambda T, and on the y axis we have the parameterized black body emissive power E b lambda divided by n cube T to the power 5. So, when we do this, what we observe is that all the curves on the left hand side for different temperatures, they basically merge together in a single curve. So, we have a single curve for all the temperatures, a single curve, basically all the curves for different temperatures, they collapse into a single curve. Now, this curve has been basically studied by many researchers in respect to solar spectrum. Okay. And solar spectrum we know it behaves like a black body emissive power, and it is at 5770 Kelvin. On this curve I have also shown you some approximate relation. So, the black body emissive power was first given by Max Planck, but researchers have been trying to fit solar spectrum even before Max Planck. So, there has been a significant work by Wiens and Rayleigh-Jeans. As we see that they tried to predict the spectrum versus wavelength, but the accuracy is very limited. Although the agreement by Wien's law is pretty much in good agreement, but the Rayleigh-Jeans spectrum is significantly in error as compared to the actual Max Planck spectrum. So, we will basically use this Max Planck black body emissive power for solving our calculations. To solve the problems, we need to calculate total black body emissive power, that is how much energy basically a body emits in its entire spectrum. The spectrum may have different ranges, visible spectrum, ultraviolet spectrum, infrared spectrum. So, we are interested in how much energy, total energy is emitted by a body in all the wavelengths, and we sometimes are also interested in finding how much energy is emitted by a body in some part of the spectrum, let us say only the visible part of the spectrum, or let us say just the infrared part of the spectrum. So, total emissive power of a black body, it can easily be calculated by integrating the spectral emissive power, black body emissive power, integrate it over all the wavelengths. So, here I have used the integration from 0 to infinity just to represent that we are considering the smallest wavelength possible and the largest wavelength possible. So, we are integrating over all the wavelengths, and when we integrate this black body emissive power, that is the Planck function over all the wavelengths, what we get is basically n square sigma t to the power 4, and this is something you are all familiar with, this Stefan-Boltzmann law, and the total black body emission power is basically proportional to t to the power 4. Okay. So, varies with t to the power 4. Okay. Unlike conduction and convection, which are basically linear phenomena, the radiation varies non-linearly with temperature, and the variation is power 4 with temperature, and that is why the variation, the temperature, at high temperature we need to study radiation, because at high temperature the radiation energy significantly dominates over conduction and convection because of this power 4 effect. So, radiation will be very important phenomena at high temperatures. The Stefan constant, the Stefan-Boltzmann constant sigma is defined in terms of radiation constant C1 and C2 by this relation pi to the power 4 C1 and 15 C2 4, and the value of Stefan-Boltzmann constant is 5.670 10 to the power minus 8 watt per meter square, temperature power 4. Okay. So, this is the total black body emissive power integrated over all the spectrum. Now, as I said, we sometimes need only the energy emitted within a given spectral range, okay, either between 0 to lambda, as I have done in this fractional black body emissive power, or sometimes we may need emissive power in the range lambda 1 to lambda 2. So, fractional emissive power f n lambda t is defined as integrated emissive power between a range 0 to lambda, that is 0 to lambda, E b lambda, T lambda, D lambda, and then divided by the total emissive power, which is basically sigma t to the power 4. So, the denominator is nothing but equal to n square sigma t to the power 4. So, this ratio is called fractional black body emissive power, that is the amount of energy emitted by a black body, okay, in a given wavelength range varying from 0 to lambda. So, this is the fractional emissive power of a black body. Now, if you are interested in finding what is the amount of energy emitted between lambda 1 and lambda 2 in two different wavelength regions, all you have to do is just find out E lambda 1 to lambda 2, that is the amount of energy emitted by a black body between these two spectral range will be equal to f n lambda 2 t, that is the amount of energy emitted between 0 to lambda t minus f n lambda 1 t, that is the amount of energy emitted within the range 0 to lambda 1. So, difference between these two will be the amount of energy emitted between lambda 1 and lambda 2. So, we do not need to calculate these integrals again and again, these have been calculated by researchers. There is a small simple program available, one can use that simple program and tabulate these values in a tabular form. So, for example, this particular table taken from the book by Michael Modest gives you the table of fractional black body emissive power as well as the spectral emissive power. So, the first column gives you the value of n lambda t in micron Kelvin. The second column give you the spectral emissive power at that particular wavelength in the of course the parameterized form, and the third column gives you the fractional black body emissive power. So, this is the emissive power between a given wavelength range 0 to lambda divided by total black body emissive power. So, we will use these tables to solve different problems. So, let us solve one problem on the concepts that we have learned so far. So, in this problem we have to find out the temperature of a black isothermal sphere. So, there is a isothermal sphere whose temperature is constant and it is suspended in orbit around the earth. Okay. So, the sphere is exposed to solar radiation and we have to find its temperature. So, the temperature of this sphere will be found based on the radiative equilibrium, because the only energy this sphere is receiving is from the sun. So, it is receiving the energy from the sun and it is radiating energy back to the atmosphere, that is a vacuum in the space. We will do the same problem again by assuming that the sphere absorbs radiation only in the spectral range 0.4 micron to 3 micron. So, we will solve these two problems and see how the temperature of the sphere is affected when the sphere does not absorb all the radiation, only a part of the radiation is absorbed by the sphere. So, let us solve this problem. So, the first part of the problem is for the black sphere, where the sphere absorbs all the radiation. So, we will do an energy balance. First of all, we write the absorbed energy by the sphere is equal to emitted energy by the sphere. So, we have some energy absorbed and some energy emitted. Now, solar constant is known, that is the amount of radiation coming from sun is known, and it is called Q solar. This is equal to 1353 watt per meter square. Okay. This is the heat flux, the radiative energy that is coming from sun, okay. And we can assume that the radiation energy is coming from single direction. So, we have this radiation energy, this is Q sol, and this is the sphere that we have basically receiving the energy. Now, the projected area of this sphere is given as the projected area of sphere is equal to pi r square, where r is the radius of sphere. So, total energy absorbed by the sphere is equal to Q solar times pi r square. Okay. The radius can be anything. Okay. So, the total energy absorbed by the sphere is Q sol into pi r square. Now, Q emitted. So, just keep in mind that this sphere is black, okay, it is black. So, it will emit radiation as per this law sigma T to the power 4, and then its total area, that is 4 pi r square. So, total sphere area, surface area of the sphere is 4 pi r square, and total energy emitted by a black body is sigma T to the power 4 as per Stefan Boltzmann law. So, then we equate, so we get Q sol into pi r square is equal to sigma T to the power 4 times 4 pi r square. Okay. So, actually we do not need the radius value. So, radius value basically cancels out, okay, and we do not even need the value of pi is also cancels out. So, what we get is temperature is equal to Q sol divided by 4 sigma power 1 by 4. Okay. So, this is the temperature of the sphere. Just by radiative equilibrium between the solar radiation and this sphere, the temperature of the sphere can be calculated, and when we do this, this value comes out to be 278 Kelvin, okay, which is around 5 degree C. Okay. So, this is the first part of the problem, where we have to find out the temperature of the sphere, assuming that the sphere behaves like a black body and it absorbs the entire radiation over the entire spectrum. It emits radiation over the entire spectrum. Now, in the second part of the problem, what we know is that it absorbs radiation only in the 0.4 micron range to 3 micron range. So, we will do the same thing again. Let us do this again. So, Q emitted, now it will be equal to as we discussed earlier, f n lambda 2 t minus f n lambda 1 t, where lambda 1 is equal to 0.4 micrometer and lambda 2 is equal to 3 micrometer. Okay. So, we have to calculate this f function, and then we will be able to calculate the emitted energy. So, total energy emitted will be, Q emitted will be equal to f. Now, we are talking in terms of vacuum. So, we can take refractive index n to be equal to 1. Now, lambda 2 is so 3 micron, and we have to multiply by temperature, we do not know the temperature as yet, okay, minus f 0.4 micrometer into temperature. Okay, so this is the relation, and Q emitted will be basically we have to multiply this relation by the surface area 4 pi r square, and we have to multiply by the sigma t to the power 4. So, this is the surface area of the sphere multiplied by sigma t to the power 4, okay, and then this fraction f 3 t minus f 0.4 t. Okay. So, this is the amount of energy that is emitted by the sphere. Now, let us see how much energy is absorbed. So, energy absorbed by the sphere will be also in the same range. So, we multiply by area pi r square, okay, and then we multiply it from lambda 1 to lambda 2, okay, q solar. Now, we have to take solar spectrum, okay, lambda, okay, and then we have to multiply by d lambda. Q absorbed is equal to pi r square integral from lambda 1 to lambda 2, and we write q sol lambda as equal to q sol E b lambda over sigma T sun power 4 d lambda, where we have assumed that the spectral variation of solar flux is proportional to the black body emissive power of the sun. That means q sol lambda is proportional to E b lambda, because sun behaves like a black body at a temperature of 5777 Kelvin. So, we can replace the spectral flux with the black body emissive power of the sun at the temperature of the sun equal to 5777 Kelvin. So, in other words, we have written q sol lambda by q sol is equal to E b lambda by sigma T sun power 4, where T sun is 5777 Kelvin. Now, our Q absorb becomes pi r square integral lambda 1 to lambda 2 q sol by sigma T sun power 4. This quantity is independent of wavelength E b lambda d lambda. So, this quantity is independent of wavelength and we can take it out, and all we are basically left with is pi r square q sol f lambda 2 T sun minus f lambda 1 T sun, where f is basically the normalized black body function for wavelengths lambda 1 and lambda 2. Now, we do an energy balance on the sphere, that means Q emitted is equal to Q absorbed, and we get 4 sigma T power 4 f. Now, lambda 2 is 3 micron. So, 3 times T the temperature of the sphere minus f 0.4 micron temperature of the sphere is equal to q sol. The pi r square will cancel out from left hand side and right hand side, and we get f of 3 times T sun minus f of 0.4 T sun. So, if you look at this equation, this is basically a nonlinear equation in unknown temperature T. Why it is a nonlinear equation? Because this function f depends on power 4 of the temperature, and this equation cannot be solved directly. We can solve this equation either iteratively. So, we will apply this an iterative method to solve for unknown T. And when we do that, we get the temperature of the sphere as around 600 Kelvin. So, next we move to the important concept of solid angle. Just a thought experiment. When we stand in front of fire, we see a lot of heat, but when we are standing at the same distance, but at an angle to the fire, the same amount of radiation does not reach us. Okay. Similarly, a hot surface, a hot metal plate appears of a different color when seen from an angle, while it appears of a different color when seen normally. So, basically the idea that comes to our mind is that radiation probably does not behave in the same way in all the directions. In some direction it behaves in a different way. Okay. So, that is what basically it is. Solid angle basically defines the directional dependence of radiation. So, what we basically mean by solid angle is it is basically in spherical coordinates. In spherical coordinates we have basically two angles. One is the polar angle taken from the normal, okay, this is the polar angle, and one is the azimuthal angle taken from some arbitrary direction in the given plane. So, psi is basically the so theta is the polar angle and psi is the azimuth angle. Okay. So, we define basically the solid angle as the so for if we have any plane of area, let us say dAj, and we have some energy leaving this plane dA. Okay. So, there is a plane dA and there is a plane in space dAj. So, solid angle is basically defined as the ratio of this plane, projected area of this plane in the direction joining the plane P to the plane dAj. So, the line joining this is given represented by the vector S cap. Okay. So, S cap is the direction of the of this plane dAj. Okay. So, we define solid angle as the projected area dAjP. Okay. This is the projected area onto this direction, okay, divided by the distance of this plane, projected plane, from the point we are basically looking this plane. Okay. So, we are trying to find out the solid angle of this plane dAj from point P, which is on the plane dA. Okay. So, the solid angle by which this plane dAj is seen from P is equal to dAjP, where dAjP is the projected area divided by distance S square. So, S is the distance of this projected plane from the point P. So, this is the solid angle. So, solid angle basically gives you the idea of the directional dependence of radiation. Now, now this projected area can be of unit magnitude. So, that what I mean by that is this projected area need not be here, it can be on the sphere, unit sphere. So, if this projected area is taken at the unit sphere, okay, that is the sphere of radius 1, then this solid angle omega will simply be equal to projected area. So, Aj prime is basically the projected area on unit sphere, that is the sphere of radius 1. So, when we take this projected area on unit sphere, then the solid angle will be equal to the projected area itself, and this solid angle is basically this area. This is the projected area that I have marked, given by dAj double prime, okay, and this magnitude is equal to sin theta d psi, and this is equal to r d theta, that is r is equal to 1. So, this is equal to d theta and this magnitude is sin theta d psi. So, in that sense dA prime double prime is equal to r d theta times sin theta d psi. Now, r is equal to 1. So, dA prime double prime is equal to d theta d psi sin theta, and that is basically the small solid angle. So, d omega is the small solid angle by which this small area dAj is seen from point P. Okay. So, this is a small solid angle d omega, and we can represent this solid angle in terms of azimuthal angle azimuthal angle psi and polar angle theta. So, as I told you that radiation depends on angle. Okay. So, emissive power does not give us any idea how the intensity or radiative intensity emitted from a surface behaves in a given direction. Okay. So, it gives you total amount of energy emitted per unit area, but it does not give you how much energy is emitted in a given solid angle. So, to basically include the effect of solid angle, we define what we call radiative intensity. Okay. So, radiative intensity is basically the energy emitted per unit time per unit area in a given solid angle, that is the energy emitted per unit time, that is watt per unit area meter square and per unit solid angle steradian. So, the units of solid angle I need to mention is steradian. Okay. So, so intensity will have units watt per meter square per steradian. We also define spectral intensity just like we defined spectral emissive power. So, spectral emissive power is radiative energy emitted in a given solid angle per unit area in a given wavelength. Okay. So, the units will be here watt per meter square steradian angstrom, where angstrom is the unit for wavelength. Okay. Now, one thing you should basically remember is when we talk area normal to rays in the intensity, what we are basically talking is not the area from which the radiation is emitted, we are talking about area which is normal to the intensity. So, if you have this surface and it is emitting radiation in this solid angle, okay, then we are talking about this area which is normal to the rays. Okay. We are not talking about the area from which the energy is emitted. So, we are talking about area normal to the rays. So, intensity is always defined in terms of area normal to the direction of propagation of radiative intensity. Okay. So, this thing sometimes is confusing, you should keep in mind that radiative intensity is defined as the energy emitted per unit area normal to the direction of propagation of the radiation. Now, definitely the two are related, radiative intensity and emissive power are related. Emissive power gives you total energy emitted from a surface, while radiative intensity gives you energy emitted in a given solid angle. So, so we can relate, so amount of energy emitted in a given solid angle is related to as per the definition of intensity, area projected, that is area normal to the rays and multiplied by small solid angle. So, this relation on the right hand side, intensity multiplied by projected area multiplied by small solid angle gives you amount of energy emitted in a given solid angle. When we integrate it over all the solid angles, it should give us the emissive power. So, we can write intensity Is, which is in a given direction, dA prime dAp, which is the projected area, d omega the small solid angle, and integrate over all the solid angle, that is 2 pi. So, when we do this, we get this relation. So, we have written d omega in terms of theta and pi. So, we have sin theta d theta and d psi. So, d omega we can write sin theta d theta d psi, that is what we have done. Intensity depends on polar angle and azimuthal angle. So, instead of writing intensity as a function of S cap is the propagation, as we see in this picture also, intensity in the particular direction. So, this is the direction S cap. So, this direction can be written in terms of polar angle and azimuthal angle. So, I is a function of theta and psi, and then dA cos theta is basically the projected area. So, we are not taking dA, we are taking the projected area. So, projected area dAp is equal to dA cos theta. So, this is the projected area. Okay. So, when we do this, we get the emissive power. Okay. And for a black body, as we will see later, the intensity does not depend on theta and psi, that is it is independent of direction, and we can take it out, and this will be equal to, so black body emissive power, we will prove this in next lecture also, will be equal to intensity taken out, because it is not a function of theta and psi, and then we just integrate over cos theta, sin theta, d theta and d psi, and this will be equal to pi times Ib. So, black body emissive power and black body intensity are related with this relation Eb is equal to pi Ib. Okay. So, we will go into this detail again. Okay, thank you. In the next lecture, we will cover the fundamental laws of radiation like Kirchhoff's law, Wien's displacement law and Planck's law. I thank you all for giving your time to this lecture.